In 4.7 we're going to look at regression to the mean, and I think this will be best outlined with an Excel file, which I'll show in a second. But first, basically what this says is our predicted z hat in the y. And what that means is, so we actually did an example like this in class. We tried to predict y values based on the correlation coefficient r and the corresponding x values and standard deviation. Well, you can remove standard deviation if you convert your x and y to z-scores, and we've done this in the past. And so we would get a predicted z hat, which is the z-score we would predict for the y-coordinate, and that's just equal to our correlation coefficient times the z-score for our x-coordinate, whichever. And since we could have multiple x values, we would get multiple z-x's. R is a constant for our data, and so we would get multiple predicted z-hats for the y. So let's look at Excel and see what this means. So here's a chart, and basically I have the correlation coefficient over here. Let me highlight it so we can see it. And then we have zx. Now we would get this from the data, but I just picked increasing numbers from 0 to 2. And then we would get our corresponding zy hat by taking our correlation coefficient times each of these zx values, and that's how we get our corresponding zy hat values. And so what we'll find is if your correlation coefficient is 1, that means x and y are correlated at 100%. Then if my zx is 0.5, my zy hat is 0.5. If my zx is 1, my zy hat is 1. So you can see it's basically a 1-for-1 line for points. Now let's see what happens as we play with this correlation coefficient. If I make it 0.9, now before I hit enter, pay attention to the scale. So our scale right now is from 0 to 2.5. It's a 1-for-1 zx is zy hat. When I go 0.9, what we get is, notice how this axis now is different. It goes from 0 to 2, and when zx is 2, zy hat is 1.8. It's a little bit lower. When zx is 1, our zy hat is like 0.9. It's a little bit lower. So let's do this even more. Let's go down to 0.5. And as we recall, the lower the correlation coefficient, the closer it is to 0, the worse our data is as far as being correlated. So our data would go from the dots being in a straight line to the dots being all over the place like a cluster. So if the data doesn't look very straight, you would get zx's, notice if zx is 1, zy is only 0.5. So what's happening is as our correlation coefficient shrinks, our zy values are getting closer to 0. They're getting smaller. In fact, when zx is 2, zy is only 1, so it's half as big as zx. And then if we go really small, like 0.1, notice the axis change. All of our data points are, we're going to predict all of our z-scores for the y component to be less than 0.2. And so what they're doing is they're all shrinking and getting closer to 0. Well, 0 of a z-score is a special thing. It's the mean. So all of our y values, our zy's, are getting closer to the mean, or z equal to 0. And so that's really what it equates to, is that we're saying since r here is always a number less than 1, less than or equal to 1, our predicted z-score for the y component will always be less than the z-score for our x component. And they actually get closer and closer to the mean. And that's what 4.7 is all about.